and I am an AI development engineer at Altera working on the FPGA AI Suite. My talk today is just going to be an introduction to the FPGA AI Suite of tools. But before I get started, I'd just like to get a sense of who we've got in the audience today. So if we can do a quick show of hands, could you please raise your hand if you are an existing FPGA designer? All right, a lot of you, probably more than half, maybe 2/3. And can you raise your hand if you are thinking about integrating AI into one of your future FPGA designs? Oh, wow, lots of you. So good news, you're in the right place. If you want to integrate AI into your design, then we recommend that you start with the FPGA AI Suite. And if I could just get the technicians at the back, can you switch out these presenter slides for the separate deck of presenter slides that we prepared? These are the default speaker notes. I don't think there's anything in here. All right, thank you very much. So going back, if you want to integrate AI into your FPGA application, the place to start is with the FPGA AI Suite. This is the quickest and easiest way to add AI to your FPGA. So if its capabilities fit your application, then that is great news. So with that being said, as you saw in Ilya's talk just now, the world of AI is very broad and very diverse, and it's evolving extremely rapidly. So FPGAs are great for that, right? In the FPGA world, we love areas that are evolving very rapidly. But it should come as no surprise to you that there are many different approaches for integrating AI into your design. And the FPGA AI Suite, while it is very capable, and while we are adding new capabilities all the time, definitely can't do it all. So if the AI Suite is not a good fit for your application, it's important to understand that there are many different paths to building an AI application on the FPGA. You can go the bespoke hardware route. So if what you want is a custom hardware accelerator built in the FPGA fabric, which is what the FPGA AI Suite is going to give you, but if the FPGA AI Suite won't work, you can go the traditional RTL route, right? Doing a traditional FPGA design through Quartus. You can also use one of our high-level design tools like DSP Builder or SYCL HLS. If your AI model is actually really small, you might not even want to waste any fabric area on that at all, in which case you could run the entire AI model on the CPU, whether the ARM SoC or a Nios 5. And actually later in this breakout session, my colleague Jim will be giving a talk on TinyML, which will let you do exactly that. We also have a number of Altera partners who offer AI solutions. So please talk to your Altera FAE or rep. But we do recommend that if AI is what you want to do, the place to start is to evaluate whether the AI Suite will meet your needs. So with that, in the talk today, I'm going to talk about building an AI accelerator using the FPGA AI Suite tools, and just give you a high-level overview of how you use these tools and how the whole thing works. I also want to touch on some of the ease-of-use features that we've added to try to get it to be as quick and easy as possible to get that AI into your application. And then in the next talk, right after mine, my manager, Tim, is going to walk you through a demo that'll make all of this concrete. He'll be showing you how to get a real-world AI model and how to optimize it for an Agilex 5 device. So definitely stick around for Tim's talk. For those of you who might be very new to AI, I just want to give you a brief overview of what I mean when I say adding AI to the FPGA, and also just take the opportunity to give you some definitions for things that are going to come up again and again throughout my talk and probably other talks today. So for some of you, this might be quite basic, but let's go through it. So a deep learning graph is what defines the structure of the arithmetic that an AI model is going to perform on its inputs. Right? This graph is structured in many layers, and every layer is going to produce some hidden intermediate result, with the very final layer of the graph is going to be generating the actual AI model's output. Right? A typical graph will have many, many layers, and the layers vary significantly in their computational requirements, both in the type of arithmetic that they're performing, right? Whether it's linear, like a convolution or a matrix mult, or nonlinear, like softmax, ReLU, maxpool. There's a whole whack of them out there. And also in the amount of arithmetic. So in a typical graph, the layers will vary quite dramatically in their computational requirements. You'll have really big ones, really small ones. And this character of these AI graphs makes it comparatively difficult to accelerate. Every layer of the graph contains a very large number of tunable numerical parameters, which are called weights. And when we talk about the process of training an AI model, that is the process of iteratively converging on a set of weights such that the AI model will perform whatever task that it was intended to perform within some acceptable accuracy. Right? So this training process is an offline process. And it goes, and once it's complete, what we do is we freeze the weights. Right? And the graph and the weights together become what we call a trained AI model. Right? And this trained AI model is what gets deployed into the product. When the trained AI model is running in the product, right, with the AI doing whatever task that it was intended to do, that computation that's going on sort of in real time is what we call AI inference. So the inference computation is what's going to be happening on our FPGA. So let's just take a step back for a moment and think about the personas who are involved in what I just described. Right? On this side, we have the data scientist. Right? The data scientists are the guys who have PhDs in CS, and they pick the graph structure of the model, they train it, maybe they refine that graph structure a little, they train it some more, and at the end of the day, what they produce is a trained AI model that is capable of doing whatever AI task we set out for. Right? Now on this side, we have the FPGA designer. Right? We've got us. And what we need is some kind of AI inference IP that can run the AI model, and we need to integrate that into the rest of our design and do, all of the usual FPGA design stuff. And bridging that gap between the world of the data scientist and the world of the FPGA designer is actually quite a hard problem. And it becomes harder still if you're going to have some kind of iteration between the two sides, which we're finding is quite typical, right? Maybe you go to, you put the thing on the FPGA and it takes up too much area, so maybe you're going to refine the model and there's going to be some back and forth. But bridging this gap between these two worlds is exactly the problem that we've set out to solve with the FPGA AI Suite. So, how does it work? This is a high-level diagram of the steps that are involved in getting from a trained AI model to AI inference running on your FPGA. And I'm going to walk you through this diagram piece by piece. And we are going to assume throughout that our starting point is with this trained AI model. Right? So either the data scientists in our company have prepared a proprietary model, they've given it to us, and it's our job to integrate that into the FPGA. Or maybe you just go online and you pick up one of the very powerful open source models that's available. But we're starting with this trained AI model. So let's take a look at the first step, which is the OpenVINO model optimizer. So the first step is to convert your trained AI model into what's called the OpenVINO graph format. Right? So the trained AI model that we start with is going to be expressed in the format of an AI framework. Right? The most popular and best known of these are TensorFlow and PyTorch. You've doubtless heard of these. But actually, all of these are in common use. And what the FPGA AI Suite needs as its input is this OpenVINO graph data format. So you can really think of this step as a format conversion, like from bitmap to JPEG, but it's a bit more than that. I'll get into that. But the key to know is that you really only need to do this once. Of course, unless your model changes, right? Then you'll need to do it again. The word OpenVINO is showing up an awful lot on this slide. And if you're anything like me, the first time I encountered this stuff, you're probably wondering what the heck is OpenVINO and what does it have to do with the FPGA AI Suite? It's a pretty common source of confusion. So OpenVINO is an open source toolkit that's developed by Intel for deploying deep learning models into accelerator hardware. Right? This is for many different kinds of accelerator hardware, not just FPGA. So Altera is leveraging these open source OpenVINO tools for the FPGA AI Suite. So they're integrated, right? So consider the OpenVINO set of tools as separate from the FPGA AI Suite, but they're very tightly coupled, right? OpenVINO is a mothership in-cell invention that we're leveraging. So the OpenVINO Model Optimizer is the tool that we are using here. And it is doing two things for us. So first is that format conversion that I talked about. And the format conversion is important because it gives you, the user, the flexibility to use any of this wide range of AI input framework formats. And all of these are supported by the FPGA AI Suite, thanks to us using OpenVINO as a front end. As the name implies, the OpenVINO Model Optimizer is also going to be applying some basic optimizations to the AI's graph topology. It's just doing this to try to reduce the computational requirements on the accelerator. It's doing this, by the way, without modifying the numerics. We're not going to lose any accuracy in this optimization. But the optimizations that the Model Optimizer does are pretty generic. They're not specific to any particular hardware backend. We're going to be doing a lot more FPGA-specific optimizations inside of the FPGA AI Suite itself. All right. So we have our pre-trained AI model, and we've converted it to this OpenVINO graph format. So let's dive into the actual FPGA AI Suite. All right, so this diagram is showing you the basic flow of what's going on with the FPGA AI Suite. And it's divided into the top and bottom. And what you'll see is that there are two different tools being used here. They're both part of the FPGA AI Suite, but they are separate tools. So at a high level, what we're going to be doing is we're going to be generating a custom hardware accelerator to your specifications, which will become an IP on your FPGA. And then we are going to compile your AI model to target that new custom hardware accelerator. All right, so let's start on the bottom with the IP generator flow. This thing here is the architecture description file, and that is what encodes the specifications for your custom hardware accelerator. I like to think of the FPGA AI Suite IP as being a very, very, very parameterizable IP. And this .arch file is what describes that parameterization in human-readable format. So the IP generator is just a tool that takes in the architecture description file and pops out the FPGA AI Suite IP. Right? You might be wondering about these parameters, right? What kind of information the .arch file encodes and what kind of knobs you've got available for you to twiddle. And the answer is there's a lot of stuff in there, but at a high level, the .arch file encodes information about the dimensions of all of the different compute engines inside of the FPGA AI Suite IP and the dimensions of buffers. So that really determines a lot of what is the trade-off between the area and the performance of the IP. Within the FPGA AI Suite, we have a number of different special purpose compute engines, which you can turn on and off and configure through the .arch file. And remember, graphs vary dramatically in their compute requirements. So whether you need certain compute engines in there or not will depend on your application. The .arch file encodes the numerical precision at which the IP is going to operate. And the .arch file has also some information about how the data movement is going to work, whether you're going to be drawing inputs in from DDR, whether you're going to be streaming them in, right? And a whole lot more. But the key thing to remember is that the bottom of this graph produces for you an IP, right? And that IP is now ready to integrate into your design, right? No different than if you had generated the IP through the IP catalog. All right, now let's talk about the top half of this graph. And the top half of the slide shows the compilation flow. All right, so what we have done is we have created a custom hardware accelerator, and now we're going to need to compile our AI graph to work on that accelerator. So the compiler needs two inputs. One is the .arch file, right, and that's going to tell it about the specifics of the accelerator that it needs to compile for. And the other is that OpenVINO graph data that we previously generated, which tells it all about the computation that it needs to map onto the hardware. The compiler is then going to map your computation to run optimally on your AI IP. And it's going to do this graph layer by graph layer. There's a lot of cool stuff going on in the compiler. It's really going to try its very hardest to optimize your throughput by maximally utilizing every cycle, trying to use as much of the compute hardware that we instantiate as possible. Another thing it does is sometimes graph layers that are very large are too big to fit in buffers within the IP. So the compiler is responsible for figuring out an optimal way to slice and dice those graph layers and then schedule all the pieces so that they run through the IP. And again, the objective is always to try to keep every DSP, every compute element inside of that IP busy as much as possible. But at the end of the day, what the compiler is going to do is generate an instruction stream which tells the FPGA AI IP how to behave, right? And that instruction stream I've indicated here is called a compiled graph, not a very creative name. You'll also hear it sometimes called the configuration or the config. And all right, and the other thing that the compiler is going to do is it needs to figure out if there are any layers in your graph that cannot be run on the FPGA AI IP. Right? This can happen if you have decided not to include a compute engine that you need for that specific graph layer. It can also happen if the FPGA AI Suite just doesn't support that kind of layer yet. Right? We're adding new ones all the time, but it does happen. And if it happens, it's not a big deal. The compiler will flag that layer as one that we cannot do. By the way, you might choose to omit a compute engine that you do need just because you don't want to spend area on it, because you can just run that layer on the CPU, and the compiler will figure that out, and the graph will still work. So this is actually a really important point to understand. Right? You can compile within the set of graph structures broadly that the FPGA AI Suite supports. You can really compile any graph for any IP. Right? It might not be particularly optimal. It might not be the fastest, but it will work. Right? What this means is that once you've generated an FPGA AI Suite IP, you can change your graph. You don't have to change the IP. You can run multiple graphs on one IP. Right? The key here is that the IP is not specific to any particular graph. I want to take a moment to highlight some of the flexibility that we've built into the way that this tool works. So it's kind of obvious, but you get an IP, and that means that you have control over how that IP integrates with the rest of your design and how it interacts with other elements of your design. We're not trying to take over your whole design. You also have a lot of control over what goes into this IP, right? You have control over what IP fabric resources it'll consume in particular, right? So you can decide how much of your total floor plan area that you want to devote to an AI core, right? And as I said earlier, once you've got that AI core and it's in your design, what you have is a generic hardware accelerator that you can use for many different AI graphs. So again, we really designed the FPGA AI Suite with flexibility in mind. Now, before I leave this slide, I want to highlight one more thing. So while I have shown this flow as a feed-forward process, hopefully, it's becoming clear to you that there's going to be a lot riding on what actually goes into that architecture description file, right? The architecture description file and what parameters you choose in there are going to determine the performance that you're going to get for a particular graph. They'll determine your resource utilization in the fabric, how you get data in and out. So you should expect that you're going to have to do some iteration to iterate on that architecture description to get it tuned to be optimal for your particular application. All right, we actually have some really awesome tools to help you with that process. And again, another plug for my manager, Tim's talk coming next. He will be walking you through how to use some of that. All right. So with that, let's talk about what actually happens when we go to run inference on the FPGA. All right, so on this slide, on this side, we have our FPGA AI Suite IP. It's been integrated into your design. It's been compiled through Quartus. It's programmed into the fabric. It's sitting on the FPGA. It's ready to go. All right, and on this side, we've got the OpenVINO Runtime inference engine. All right, the inference engine is a lightweight piece of control software. It sits on the CPU. That CPU could be an attached x86 host. It could be an ARM SoC. It could be even a Neos 5, if you want. And the job of the inference engine is to orchestrate the inference computation layer by layer. Right? So the OpenVINO runtime inference engine needs two things. Obviously, it needs that instruction stream that we generated when we compiled the graph in the last step. And it also needs the OpenVINO graph data. Remember that data structure that basically describes the graph topology and all of the training weights, which we generated in the very first step. So OpenVINO inference engine needs both of those things. And now what's going to happen during inference is that the graph computation is going to take place over many sort of passes or recirculations through the IP. All right, the FPGA AI Suite IP has what is called a temporal overlay architecture. And by temporal, we mean that the graph computation takes place over time. You're reusing the IP many times to do all the layers or chunks of layers. And the overlay basically means that we've created a programmable hardware on top of the programmable hardware of the FPGA fabric. All right, so with every new layer, the inference engine will be configuring that IP with an instruction stream, and the overlay will change its shorts and will be performing whatever arithmetic is needed by this specific layer. Right? And as I said earlier, if there are layers which the IP does not support, then the OpenVINO inference engine simply executes those layers' computation on the CPU. I should also tell you a little bit about the data flow during inference, right? So in this picture with the little cartoon here, we kind of implicitly assume that we've got some sort of image classification problem on the go. So that image data can be queued up in DDR, and you can just sort of pass a pointer of it to the FPGA IP, say go, and it can dump its results back to DDR for you to retrieve. We also support a streaming configuration, so you can stream the data into the IP, and then the results will pop right out. So yeah, in a nutshell, that is how inference works when you're using the FPGA AI Suite. All right, I would like to touch a little bit on the usability features that we've built into the FPGA AI Suite. Right, and this is, I guess as my title implies, these are here to try to make things as quick and easy for you as possible. And the features I want to highlight are features that enable rapid iteration in software. So by this, what I mean is that you want to be able to do as much of the work to optimize the FPGA AI Suite IP and validate your solution without needing Quartus in the loop and without even necessarily needing to bring up a board. Right? The Quartus guys are awesome, and they're making Quartus fast all the time. But if you've got a lot of iteration cycles to do, and you need to do a full Quartus compile and a board bring up every time, that's going to be a lot slower than if you can just instantly try things in software and see what sticks. So we provide tools for area estimation. If you generate an IP, we'll give you a pretty good estimate of what area resource utilization you can expect it to take up in the fabric. We provide a performance estimator. So when you compile a particular graph through the graph compiler, it'll give you its best guess of the throughput that you can expect. So how many inferences can be performed per second. And we also have a bit-accurate software emulator. So this is a tool that enables you to validate your numerical results in software. The FPGA AI Suite IP does some trickery with numerical precision. So you will not get identical results to what you would get if you just ran an FP32 on a CPU. You'll get very close results, but if you need to validate that the accuracy is suitable for your needs, this software tool will give you, a bit accurate, identical to hardware result for what you should expect. And lastly, my favorite of these rapid iteration tools is an automatic arch parameter optimizer. So we have this little tool, and you give it a starting point architecture file, and you give it some targets, either a performance metric that you're trying to hit or an area target that you want it to fit into. And then it'll go off and do a bunch of work, and it'll try to come up with the optimal arch file, right, to save you a lot of that iteration. On this side, we also provide quite a significant range of example designs to just make your life easier when it actually does come time to go to hardware and to integrate your IP. So we provide example designs that showcase a range of different system configurations. So now that you know a little bit about how the FPGA AI Suite works, let's take a look at some of the application examples. There is a huge amount of work being done right now in the industry to apply AI to solve all kinds of novel problems. And I want to just highlight a few of the areas where the FPGA AI Suite has been used by Altera's customers. In the industrial space, we have a neat application where AI is being used on the assembly line for anomaly detection or defect detection. So in real time, basically it'll identify if there's a problem with one of the things on the assembly line. That's being used for a range of different processes. In video and broadcast, I think this is kind of the most classic AI application there is. We see AI being used for facial detection and recognition. You saw a demo in Sandra's talk earlier from Teresic doing just that. A really neat application in the medical imaging space is video image stabilization. So imagine you have a doctor and they have a handheld imaging device, like ultrasound or endoscope, and they're rummaging around in a patient, and there's a video stream on a screen that they're looking at. You want that image to be really rock steady. So AI is being used to improve that image stabilization algorithm. And in the wireless space, there's some very innovative work being done by Altera customers to improve signal processing results with the assistance of AI. So I'm really looking forward, hopefully, to either today or in the weeks and months to come, to hearing about some of the cool AI applications that folks in this room have in mind for the FPGA, because it's always fun to learn about how the FPGA AI Suite tools are getting used. All right, so to wrap up, if you want to integrate FPGA or AI into your FPGA design quickly, I recommend that you do check out the FPGA AI Suite. Hopefully, you'll come away from today's talk with a basic understanding of how the tool flow works and how you can use these tools to get that AI into your FPGA with a minimal of pain and fuss. Right? The FPGA AI Suite does give a complete solution for FPGA AI inference acceleration, and I would say it's almost as easy as adding an IP to your design. So to learn more, if you follow this QR code, it'll take you to the FPGA AI Suite website. We've got a ton of information on the website. There are white papers, there are videos, there's documentation. The AI Suite itself is free to download and free to use, but you do need a license if you decide to take the IP to production. So I wish you all the best of luck in your FPGA AI adventures. And remember that if your goal is to add AI to your FPGA, please start first by evaluating and checking out the FPGA AI Suite. Thank you very much.
Altera, accelerating innovators.